In this video, I'm going to attempt to cover everything you need to know about SN2 reactions in 10 minutes. Let's go. So let's start by identifying the main parts you need to know in a substance. So first of all, this is your leaving group. Typically, a halogen is your leaving group. So your main leaving groups that you're going to see are the halogens like Cl, Bri, another main one would be OTS, and then some poor ones might be OH minus, and we'll get into that. We gotta turn that bad one to a good one. So the leaving group is on your substrate, or we also call it the electrophile. This is the substrate or the electrophile is the thing that's going to get attacked, and then the other substance, which is typically negatively charged, that is the nucleophile. That's the attacker. So SN2 reaction, they involve a substrate and a nucleophile. Essentially, what's going to happen, in terms of predicting the product, what's going to happen is all you got to do is replace the leaving group with your nucleophile. The nucleophile is going to substitute the leaving group. So they're going to switch place. You're gonna get this SN2. The two means it's a bimolecular reaction. So it's a bimolecular kinetics. So that means that the rate law is going to equal the rate constant times both the concentration of the substrate and the concentration of the nucleophile. So that means that the rate is dependent on both of these. So for example, if I doubled the rate of the substrate and I doubled the rate of the nucleophile, then double the concentration of the substrate and nucleophile, then the overall rate is going to increase by 4. If I say triple the rate of this and quadruple the rate of this, then overall the rate is going to increase by 12. The mechanism is that the the mechanism in terms of how the reaction happens, everything just happens at once. So your nucleophile attacks and the leaving group leaves. And then there's also going to be an inversion of stereochemistry because of the backside attack. So let's say that we have this substrate and then we have this nucleophile Br minus. The arrow pushing is going to look like this. The nucleophile, the arrow always slides from your nucleophile. The arrow starts from nucleophile. The nucleophile attacks the carbon with the leaving group, and then the leaving group is going to simultaneously leave. All this happens in one step, and it attacks through the backside. So if the CO is pointing up, then the nucleophile is going to be coming and attacking from the bottom. Then afterwards, you're going to just change the CL into whatever attack the BR, but there's also an inversion of stereochemistry. There's going to be a changing of the wedging and dashing. So here, this was a wedge. It's now going to become a dash, and then the other product is Cl minus. Here's another example. We have our substrate with our leaving group, and then this is the nucleophile. The nucleophile is going to attack from the backside, attack the carbon that has the leaving group, and then the leaving group is going to simultaneously leave. And then we're going to have the OH, instead of now being on a wedge, is going to be on a dash because of the inversion of the stereochemistry. And then Br is going to get kicked off, so now it's Br minus. In terms of the transition state, you do need to know that the HOMO of the nucleophile will interacts with the LUMO of the electrophile or the substrate, and then the transition state will look like this. So you can focus on the carbon, and then you can have the leaving group on one side. Doesn't really matter which side. We'll just have the leaving group be on the right, and then you have the nucleophile be on the other side. So we'll have OH be on this side. And then if you think about what's attached to the green carbon has 3 things attached. It has a hydrogen that's attached, it has a alpha group attached, and a methyl group attached. And then the carbon in the middle, we just have to make it trigonal planar. So we'll just have to have one dash, one wedge, and one straight line. And then it really doesn't matter like what goes where. So we can just have the methyl group here, and then we can have the hydrogen be here, and then we can have the ethyl group here. So we have methyl here, and then we have a hydrogen there, and then we have the ethyl group down here. And then to show it's a transition state, we'll just wrap this in a bracket and then put the transition state symbol. Next, let's talk about the main factor that will determine whether an SN2 reaction will happen or not, and if it does happen, how fast the reaction happens. And that is sterics. That's how crowded the carbon of the leaving group or the substrate is, because the main way that the nucleophile gets in an attack is through the backside. So if this carbon is really, really crowded, then it's going to be hard for the nucleophile to get in an attack. So in terms of sterics, a methyl carbon is going to participate in SN2 reaction the fastest, then a primary carbon, then a secondary carbon, and then tertiary carbons. They're so crowded that it's really hard for the nucleophile to get in, that they pretty much don't interact, participate in SN2 reactions. So a methyl carbon will look like this. So you'll have one carbon, and it's going to be attached to the leaving group. So that's a methyl carbon. A primary carbon would be a carbon that's attached to one other carbon group that uh, and then a secondary carbon is a carbon that is attached to two other carbon groups. And then tertiary carbon would look something like this. You'll have a carbon that is attached to three other carbon groups. Notice that we're specifically looking at the carbon with the leaving group. So this is going to undergo an S2 reaction the quickest, and then tertiary carbons do not undergo SN2 reactions because the carbon is just too crowded for the nucleophile to attack. In terms of the energy diagrams, if you have to draw it out, let's say that the primary carbon or the methyl carbon looked like that. This is the activation energy. When you with a secondary carbon, the activation energy is going to be, primary is going to be a little higher, secondary is even higher, and then the tertiary is going to be really, really high. So remember, the larger the activation energy, the slower the reaction. So a methyl carbon is going to undergo an SN2 reaction the quickest. Next, let's talk about what if your leaving group is bad. How can I make this reaction happen? How can I replace the OH with a Br with a change in stereochemistry? Well, this leaving group is bad. OH is a really bad leaving group. We got to turn it into a better leaving group, and then the leaving group can leave while the nucleophile intact. So easy way to turn this into a good leaving group is just by protonating it. So we're going to use H, and that's going to be attached to the nucleophile. So first of all, the OH is going to grab the H, and then that's going to become water. So then now that is going to become OH2 positive. It's positive because it gained the H plus. So now that it's water, it's a much better leaving group. Then we have Br minus. Now that's a good leaving group. The Br minus can come in and attack and do the can do the backside attack. So it can attack the carbon with the leaving group, and then the leaving group can leave. And then that's going to give you the product as well as H2O. Another type of problem that you might see is how do you keep the configuration the same, but just change out the leaving group. So here I want to change out a CO with a BR, but I want to keep it as a dash. So the easy way to do this is just do an SN2 reaction twice. We're gonna have another nucleophile that's also a good leaving group attack, which are usually just a halogen. So we'll have, say, I minus attack, I minus will attack the carbon, and then kick off the leaving group, and that is going to give you the inverted product. So now we're going to have a wedge with an I, and then we can have the Br minus come in and attack there and kick that off, and then that's going to give the desired product. So if you want to keep the configuration the same, to just do an SN2 reaction twice, but make sure you use a nucleophile that's also a good leaving group. Examples are Cl minus, I minus, and Br minus. And then lastly, you need to know that polar aprotic solutions will favor, or polar aprotic solvents will favor SN2. So the most common polar aprotic solvents are DMSO, DMF, acetone, and acetonitrile, which looks like this. So if you have these solvents, then it's going to favor SN2 over SN1. And you know something's a solvent if it's over the arrow. For example, you might see something like DMSO, and that's indicative that it's a solvent. And there you have it. That's the majority of what you need to know about SN2 in about 10 minutes.